All right, so welcome everybody. And this is the fifth session in our programming principle series. So today I'm going to be talking about polymorphism mainly, and what kinds of polymorphisms we know. Just to recap quickly, in our previous sessions, I talked about algebraic data types, pattern matching, and monadic data structures. So to continue with these general concepts, we're going to cover a different one today. So I'm quite sure that everybody here is aware of polymorphism in a sense that there is something like polymorphism in programming languages. But I don't think that everybody has a clear understanding like what kinds of polymorphisms we have, as maybe the last time that we were thinking in those abstract terms were back in university, but it's something that we work on daily basis. We just maybe don't know the exact terminology. So this is to just sum it up, and let's do it. So I'll go over the kinds of polymorphisms we know. The most common one, if someone thinks about what the polymorphism is, then probably people coming from object-oriented programming background would think about subtyping polymorphism. So based on the description from Wikipedia, so subtyping polymorphism is kind of polymorphism where program elements, which are functions, usually are written to operate on elements of a supertype, or can also operate on elements of the subtype. So this is like a more complicated way how to describe inheritance. So we have interfaces, abstract classes, and concrete classes in object programming. This is an example of subtyping polymorphism. This is quite common. I'm quite sure that nobody would be surprised by this kind of code. It's in Java. So we have an interface and we have a person class which implements the interface. And what it does is that it complies with the contract, which is a single method here that takes no arguments and returns a string. And it can do whatever it wants to return a string. So it just formats the name and age here. And we have a, let's say, a polymorphic function print, which takes in any instance that implements the cool serializable interface here and just prints it out. So using the doIt method on the interface. So I can use my person object here, which compiler knows that it implements the interface, and it has the method doIt, which it can call with the runtime, can call it, and it just prints out the name and age. So this is the most basic type of polymorphism. I'd like to highlight that in Java in particular, this is executed by a dynamic dispatch. So this means that the evaluation which method in an object hierarchy is called is decided on runtime. So this is why it's a dynamic dispatch. So if I had a hierarchy of classes, each one can implement or override the method. Which one is called depends on the object passed to the method, right? And this is decided like via virtual tables on runtime. So the second type of polymorphism is parametric polymorphism, and it's a function or a data type that can be written generically so that it can handle values identically without depending on their type. Now, the important fact here is that it can handle any type. not just a subset of types, but it can handle any type. So this is what's behind the parametric polymorphism. Usually it's implemented in programming languages via generics, generic types and generic functions. I have an example here from Java again. So this is a simple wrapper class, which has a t as a type parameter, and it can get the type, it can set the type. So it's really simple demonstration of parametric data type. And this is example of parametric function. In this case, it's like a static method inside the class. But as you can see, that it doesn't have to be the same thing as the t, because this is like a standalone function in a context that takes in any object and it just wraps it into this simple wrapper object and returns it. So as I said, the important thing is that it can't do anything with the object because it's generic across all the types. So this is parametric polymorphism, and these are sometimes called the type parameters or generic types. Now the third polymorphism that I'm going to talk a bit more in detail, because it's not something that is quite clear and the terminology differs across languages, and it's about ad hoc polymorphism. As the description goes, it's a single polymorphic function can have a number of distinct and potentially heterogeneous implementations depending on the type of argument. Now this means that a function which supports ad hoc polymorphism can have different implementations based on the type that it accepts, right? Based on the type of the argument that it accepts, or a number of arguments. Now, if you think about it, then this might be method overloading or operator overloading in some other languages like C++. As an example, this is method overloading in Java. So we have a class called serializer that has 3 methods, which takes in a different type of argument. But you can look at this, that it's just a single method. It just operates on 3 different types of arguments. So this is considered an ad hoc polymorphism. Why it's an ad hoc? Like, the meaning of it is not super clear to me either. It's not about like when it's applied, like ad hoc on demand or at the point that you need it. It's more like it's not a construct of the type system of the language directly. It's just using the types and the type capabilities. That's why it's an ad hoc, like we're using the type system in a way that we implement the polymorphism differently. So back to our example, we have the instance of the cool serializer here. And it can, of course, operate on the types that are supported by the overloaded methods, right? So you can already see the flaw in this design is that if we want to support a different type, we would need to create a new implementation of the method, overload it again. So it's not like super flexible. I'd like to point out that this is a compile time static dispatch in Java, which means that at the time of compilation, the compiler decides like which method it's called, and then it's already written into the bytecode. Now, the question is, how do we write extensible polymorphic code without method overloading? And it's quite cumbersome to do so. And the answer is a type class. Now, this is not something that object-oriented people come across. and it's not easy to grasp or understand because the class itself, the term, is confusing here because we are not talking about object classes in object-oriented programming. So these terms comes from functional programming background, especially from Haskell. And the type class is basically a constraint on type parameter. So it's like a class of type, not the class of object. And so this is a form of Adhoc polymorphism. We have explicit and implicit passing of type classes to functions that require it. I'll show that in a bit. And in object-oriented programming like Java, we can achieve this functionality using a mix of generic programming, so parametric polymorphism, and subtyping in a form of type bounds. So how this looks in languages that support it fully and are not that alien to normal people like Haskell. So I picked two. It's Scala in version 3, because Scala 2 supported type classes as well, but it used one implicit keyword in different places, and it had a different meaning in different contexts. So it was quite confusing, but I think Scala 3 will get it right, or already got it right. It will be released soon. And how this looks like. So we have a structure, a case class person. Again, it's just a name and an age. Now this trait here, it's kind of like an interface in Java or C#, whatever. But it's an interface with the type parameter t. So it's a generic interface, a generic trait. And it has a single method, do it, which takes in an object of type t, or an instance of type t, and returns a string. So this is our type class, kind of. And the implementation or the instance of the type class is implemented via this syntax. So we have a keyword given, and we implement that cool serializer for type person with, and here comes the implementation of the method. We take in the person, return a string. Oh, this is just copying the immutable data structure, prepending like cool before the name, returning the string. Now we may have an implementation for that interface for number of different types. So here is the implementation for the int type, and it just returns 42. So trolling a bit. Regardless of the input here, it just returns 42 as a string. Now we have a polymorphic method or a function, print, which accepts a type argument t. So it accepts an object of type t. And here with a special syntax like using instance of that trait, we can now use the methods implemented, well, the methods declared in the interface. And now what's really important here is that when we call the print function here, and we pass along our object person, or we pass an int, we don't have to explicitly specify the implementation of the cool serializer trait, because this is taken from the context by compiler. And the context is basically a scope, what's available to that function print. So it knows that the type of the object is person. So it looks up, do I have an implementation for the trait for type person? Yes, I do. and it can like implicitly pass that implementation here. Same thing for the int type here. So if I had a print with a string type, for example, a string, any string, the compiler would not be happy about it because it wouldn't find in the scope an implementation for that trait. Now this has like really interesting implications. So we might have a generic code like our print method here, and depending on what's available in the context, it may behave differently. So you can imagine if we had like, there's another concept like type class derivation that the compiler could, based on some meta-programming techniques, create instances of this type class, or let's call it a trait here, and generate. So one common use case for this is to generate parsers or serializers for like any object graph. If each type supports that type class, then we might like compose individual parsers or serializers and produce the final result. Another example is from Rust, which kind of supports type classes, although in a different way, and they don't mention type classes at all in documentation because they don't want to confuse people with some functional programming concepts. But it's more or less the same thing. So we have a struct here, person, and we have a trait. Again, it's the same keyword like in Scala. It's trait. It's not an interface. It's trait. So it's just a config for something to implement. But this time it's not like cool serializer which takes in the object and returns a string, but it works on itself. Like so, this is usable for serializers, but not for parsers, of course, because we would have to work on a string type to produce some type, not vice versa, not take any type and produce a string. And so just a small difference here. Now, what's common is that we implement that trait for a person outside of the person object. Like normally in Java, you have to implement an interface for some class by using the implements keyword next to the class. So you can implement something for a class outside of that class. Now this is different here and here. So I'm implementing that trait for this class. When I do this, the compiler knows that the person implements this interface. So again, it's a cool feature, and since Rust it doesn't support object-oriented like inheritance in the strict sense, and this would be just an implementation of the method of this trait for a person struct. Now here is our generic function print again, and it does something similar, that it takes in an object of type T, but this is the type constraint that I talked about. So it's not just any T, it has to be like T, which is cool serializable. And so it can call the methods on this trait. So now I create an object of the person, and I can pass it to the function print, because I know that the person implements this interface or this trait why this type class instance. So I kind of mixing terms here, but probably, hopefully you get the point. Now, what we can do about this in Java, since Java is not that flexible, doesn't support like implicitly passing stuff to methods, like implicit contexts. This is the second example from Rust, where we have like a interface with just a single method. Now, what we can do about if we don't have access to the type, we don't own the type. It might come from a library, for example. Let's say that the person is a type defined in a library. We can make it like implement an interface, right? So the common pattern in Java is to use adapter pattern. So if I want a person which I don't control to implement an interface, I create an adapter here. So I take in the person object and I can use it in the method calls. Now, this is parametric function, well, type parametric function, which takes in an object of type T. And this is the type bound in Java. So this can be any type that implements the interface or extends. It uses extends both for interfaces and classes. So now I can call the method on that type. Now this could be, if you're asking why we just can't use the cool serializable here directly, which would be identical thing in that example. But using type bounds in Java is a bit more flexible, as I can use intersection types here. And there's another story if we accepted or return back a list of those types, then it comes, then there's that we would have to talk about variants like contravariants and covariants, and it would be a different story. But this is quite example and it's interchangeable. Now, if I call our print function here, I need to pass along the adapter explicitly. And the second example is that we have an interface which takes in the type of the object. It's not itself that it's serializing, it just takes in. So we can implement that for person. And now we have polymorphic function print, which takes the argument of type T and also an argument of type cool serializer T. Now this may look familiar. This is quite common in Java code bases. If you think about it, how comparators work. So we have an interface comparator, and we needed to, and for any higher order functions that's sorting data, you would need to pass along some implementation of the comparator, right? So this is similar. Only downside is in Java that it can't be pulled out from the context. I have to pass it along explicitly. But it's still, it fits the concept of a type class. So this was about polymorphism, and I wanted to touch the topic of structural typing because it's related, and how we can achieve those polymorphic functions with the support of structural typing. So what's the structural typing is about is that normally in common languages like Java, Kotlin, C#, Rust, the compiler works with the nominal typing. And this means that when it decides whether the type fits, it just considers the name of the type or the hierarchy of the types. But it's basically nominal in a sense that it's just evaluating names of the types, with the exception, which I think that functional interfaces are structural typing, because you might have a functional interface which has a single method, but it's named interface. So it has a name. But if I use it as an argument to some other function, I can pass a function, a lambda. And of course, lambda doesn't have a name, so it's structurally typed, it's structurally matched. But some other languages support it on different levels, like TypeScript, Go, and Elm. I have some examples in TypeScript. So let's see how this works. And also a word about duck typing. So duck typing is the same thing as a structural typing, but duck typing relates usually to dynamic languages, which don't have types. So it goes like, if it quacks like a duck, then it's duck, right? So if I have an object which has a method quack, then I don't care that it's not a duck, because it can quack, so it's a duck. All right, but let's take a look at the structural typing in TypeScript here. Let's start with this function. We have a function serialize, which takes in an argument of type name and age. A name and age is just a name of string and age of number. However, we have a person interface here, which has a name and age and something else. But I can happily call this serialize function with the person, even though the person doesn't explicitly extend the name and age interface. But it's not a problem for structurally typed languages, because the compiler knows that it requires not the name and age, it requires something that has a name and an age, right? And the person object has it, compiles fine, works just fine. Not a problem with that. So this is the idea of structural typing. And of course, it can go many levels deep. It doesn't have to be this flat structure. It might be like more complex structure. As long as the types match, the compiler is happy with that. There's no problem with during runtime, because those properties, those fields or functions or methods are there. Now, if we go back to our example with the serializing, let's see how this looks in structurally typed languages. So we have an interface with a single method do it. And we have a function that takes in the instance of that interface and just prints it to the, just calls the doIt method and prints it to the console. So we have an interface person here. This is an instance of this interface. Now, what I can do, I don't have to explicitly extend the cool serializable interface in person interface. I can just create a type that has the method and that can operate on a person field. So this is an object of some anonymous type that has all the properties. This is syntax for the construction of the object. So it just creates a new object that has all the fields from the person object, and I add the doIt method, and I can call the serialize with this object here because it has the doIt method and it's all that it's required from that interface. I just forgot to mention that this is cool in terms of what I told about that if we don't have access to a type or a class in Java, if it's from library, we would have to create an adapter. We don't need it now, from obvious reasons. If the person comes from library, it's not a problem. right? Because I can extend it freely. In structural type languages, these constraints no longer apply. Now, for the second example, we have the interface that takes in the type t, returns a string. Again, we have this polymorphic function. Now I have the interface again, person, an instance of a person, and how I can implement that interface. So I would just create a new type here, and I would just assign the object of this new type to this type. And it can do that because it structurally matches. Right? So I have the do it function that takes in a person and just returns a string. So not a problem here. But again, TypeScript doesn't know how to pull it from the context, from the scope, so I have to pass it along explicitly. So final words about TypeScript. It doesn't support, on the other hand, function or method overloading because of the underlying runtime, which is JavaScript. JavaScript doesn't have an option of different methods with different signatures, as it's dynamically typed, so it can accept anything. So that's why this doesn't work, and the TypeScript compiler would block this. On the other hand, we can look at using union types as a way to do polymorphic code, right? So this is the type, so it's a function that accepts an argument of type number or string. Now this is like simple implementation. It might have different implementation for different type. So this is the essence of the type classes. So we can consider this actually to be kind of a type class implementation, because we can have different logic based on the type of the arguments, but only if we can understand what's the type in runtime. And this is the end. So I'm open to questions. Hopefully it wasn't too confusing. But the main idea is that we have different kinds of polymorphisms, and we can use it differently with minor differences in different languages. If there are any questions, I'd be happy to answer them now, or just let me know afterwards. Thank you, everybody, for the attention, and we'll see you next time.
Thank you.
Thanks, Michal.
Thank you.
Bye.